From the Biot-Savart law, we can calculate that the magnetic field around an infinite wire is given by the formula B equals mu sub naught I over 2 pi r. The direction of this magnetic field is given by the right-hand rule, where your thumb represents the direction that current is traveling, and your fingers curl in the direction of the magnetic field. So the result of this infinite wire with current flowing through it is a magnetic field that wraps around it, that is, whose strength depends only on the distance. Well, and on the current, but assuming current is constant, depends only on distance. What this means is that if we take a circle that is centered at the wire, and the surface of the circle is normal to the wire, then we can say that the magnetic field everywhere on that circle is mu sub naught I over 2 pi r. Furthermore, the direction of the magnetic field is always tangential to the circumference of the circle, which means that if we integrate the magnetic field along that circle, then magnetic field is constant, the angles are constant, so dot product is constant, and so it just becomes B times the circumference, which is 2 pi r. If we look at our formula for B is equal to mu sub naught I over 2 pi r. The 2 pi r's cancel, and we're left with the integral of B dot ds is equal to mu sub naught times I. Now, consider way back in chapter 1, when we were learning about Stokes' theorems and vector fields. Stokes' theorem explicitly states that if there is some integral of some vector function dot ds over a closed loop, that integral would equal the curl of that vector function integrated over the area bound by that loop. What this means is that we can replace this term with this term, and we likewise have a true statement. Now, one more thing. This is true for just a given current. But current can be distributed out in 3 dimensions. Now, if the current is distributed in a cylindrically symmetric pattern, then we can say that it has a current density, which we call J. And we can say that the total current is the integral of J and area. And this, by the way, I've mentioned a couple times why I is technically not a vector. This is why. J is the real vector in this case, and I is the result. I does have a kind of hand-wavy direction. But getting back to this, J dot dA equals di, which means that if we integrated this over area, we would get a certain current. Now consider, this integral is now equal to the integral of this. Put them together and we get this. And would you look at that? We have some function dot dA and some function dot dA, and we're saying that their integrals are equal. Furthermore, we're saying that their integrals are equal for any path we choose, or for any area we choose, because this held true regardless of path. What that means is that we can say that this vector is therefore equal to this vector, or the curl of B is equal to mu sub naught times the area current density. This is known as Amperes Law. Now, you probably have seen Amperes Law before in Physics 2, but you saw it in this form. This form and this form are the same thing. They are just taking an application of Stokes' law. Amperes law is kind of the magnetic field analogy to Gauss's law. So recall Gauss's law, if you had a closed Gaussian surface, you could say that the total electric flux through that surface depended on the enclosed charge. Well, now we can say that the total, this isn't magnetic flux, but it's functions similarly. The integral of B dot ds is equal to the enclosed current. Now, charge can be a point, so charge gets enclosed in a volume. Current has to flow from one point to another. So we say current has to pass through a particular surface. Now, like with Gauss's law, Ampere's law is always true. However, it's not always useful. In order to really get significant use out of Ampere's law, we need to have some kind of symmetry that we use. There are a few symmetries that are commonly seen. If you look on page 237 of your textbook, it lists a few very common symmetries that make Ampere's law usable. An infinite straight line, like we did right here, and the others, you can read the examples in the text, the infinite plane of charge, infinitely long solenoids, and toroids. And I should take a moment to point out that we can still use the infinite cases even for things that are finite, as long as the distances to these objects are much, much smaller than the size of the objects themselves.